we're going to talk about finding recursively defined sequences. And recursively defined sequence is when we start with some base number, and then we're told the next one is equal to something happening to that one, plus something else, or minus something else, or there's some rules going on related to that one that tell us how to create this one. Alternatively, we might write this as an equals something happening to an minus 1 and something. And it's also possible that we have multiple previous entries. If we do, we just have to make sure we provide enough base cases that we can build right off of the get-go. The most famous example is Fibonacci's sequence, which starts by saying that A1 is 1, and A2 is also 1, and AN is equal to AN minus 2 plus AN minus 1. So for instance, A3 is A1 plus A2, which is 1 plus 1, or 2. A4 is A2 plus A3, which is 1 plus 2, which is 3. A5 is A3 plus A4, which is 2 plus 3, which is 5, and so on. In fact, it's really easy to do Fibonacci sequence by listing these 1, 1, just add these together to get the next one, add these together to get the next one, and we just keep adding them in pairs for as far as we need to go. Now the catch here is that in order to find this 13, I had to know both of these, which in turn required these and these, which goes all the way back until our base case. So we have to start at the beginning and work forward. We cannot start in the middle with recursively defined sequences very easily. So now that we know that and we're looking at this, let's look at an example. Suppose that we let A1 equal minus 4 and AN plus 1 equal 2 times AN plus 5. So if I want to know A2, that's equal to 2 times A1 plus 5, which is 2 times a minus 4 plus 5, which is minus 8 plus 5, or minus 3. A3 is going to be 2 times A2 plus 5, which is 2 times a minus 3 plus 5, which is minus 6 plus 5, which is a minus 1. A4 is 2 times A3 plus 5, or 2 times a minus 1 plus 5, which is a minus 2 plus 5, which is a positive 3, and we can just keep repeating this process as far as we care to go. But notice I have to have that base case, and then I have to work this A2, then A3, then A4, then A5. So if I asked you to find A7, you'd have to find A5 and A6 first, and then you would stop here with whatever this result was. The other piece of this that we want to talk about is honeybees. And honeybees are kind of unique because a male honeybee comes from an unfertilized egg from the queen. So it just has a female parent. But a female honeybee, a worker, comes from a fertilized egg, which comes from a female and a male. So every female has 2 parents, and every male has just 1. So let's look at this. Let's find a sequence that accurately counts the ancestors of the male honeybee. The first term of the sequence should give the number of the parents, and the second term should be the number of the grandparents, the third the great-grandparents, and so on. So let's see if we can find a sequence that does this. So if we start with a male honeybee always has just 1 female parent. The female, though, has a male and a female parent. And the male, of course, has just a female. But the female has both a male and a female. So notice we're going 1 for the base generation. This is the parent level. 2 at the grandparent level. 3 at the great-grandparent level. And if we do this one, this of course is going to give us a male and a female. This is going to be just a female. This is going to be a male and a female. And we get 5. And you notice what we're seeing right here? Next up, this looks like the Fibonacci sequence. In fact, it is the Fibonacci sequence. So the next level should be 8. We'll get 1 plus 2 is 3. 2 more is 5. 1 here. And 2 more here gives 1, 2, 3, 4, 5, 6, 7, 8. So the Fibonacci sequence, one of the places this shows up, is when counting the ancestors of a honeybee. And so this is an example of how we can find a recursive sequence when we have a recursive rule.